Today we're going to talk about the Ehrenfest Theorem, which talks about the time derivative of the expectation value of an operator, which I call A, and from now on I'll always refer to time derivatives with a dot on top. In order to do so, we need the time-dependent Schrödinger equation, which is given here, and we'll also need the Hermitian conjugate, which I already wrote down here. Note how the kets get turned into bras, and here the order reverses, as well as the change of sign for the I. We also need the general expression for the expectation value of the operator A, and we'll assume that A is independent of time, which will make calculation later a bit easier, but it's not necessary at all. And since we're going to discuss the theorem with an example, we've got here the Hamiltonian of the harmonic oscillator. Now, if we want to derive the Ehrenfest theorem, we start by writing down the derivative of the expression for the expectation value, and we take the product rule so that we get psi dot A psi plus psi A dot psi plus psi A psi dot. Since we said that our operator is independent of time, we know that the second term vanishes, leaves us with two terms, and now we sub in these expressions over here. For the first expression we need the Hermitian conjugate, and for the second expression we need the original time-dependent Schrödinger equation. So we get I of h bar psi h a psi plus psi a minus I of h bar h psi. Now let's take out the constant I of h bar. And this should be a minus, of course. So now what we can see is we have Hermitian operators, which means the h's can move into the middle, and now we see we have HA minus AH, which we recognize as a commutator of H and A, and now we can see that this expression, bra operator ket, is the same as this expression for an expectation value, so that the middle term here is just the expectation value of the commutator of H and A. And this is the general form of the Ehrenfest theorem. Now, we want to be a bit more explicit, and so we're going to apply this formula now to the harmonic oscillator, and we're going to look at the change of the expectation value of the position and of the momentum. And in all cases, we'll need to evaluate this commutator, which is going to be the hardest part. Now, if we look at the position, we will have to evaluate the commutator of h and x, which we can just write as 1 over 2m p squared n x plus 1 over 2k x squared n x. Now, the second term will vanish as x squared and x commute, but this term will not vanish, and we'll have to use a trick to evaluate a commutator that is something squared and another entity. How are we going to do this? We're going to say that if we have a squared and b, you can write it as AAB minus BAA. And now we use a trig. So you say AAB, we subtract ABA, we add ABA, so that we don't change the overall value of the commutator, and then take minus BAA from here. What we can see now is that we have here AB minus BA, both pre-multiplied by A, and we have AB minus BA, both post-multiplied by A, so that we can write AB plus commutator AB A. Now if we apply this over here, we can write this as 1 over 2m, and then we write px plus px p. And now we know that this is just minus IH bar, and we have it twice because this is the same. And so this commutator evaluates to 1 over 2m times minus 2 IH bar p, which is just minus IH bar p over m. And if we plug this now back into our equation here, we can get d expectation value of x by dt is I over h bar times minus IH bar p expectation value over m, which is just p over m. And here, why do we just have the expectation value of p when we have all these constants around? We take the expectation value of constants, nothing happens, because the only thing that changes, where we can really take an average, is of things that are variable, which in this case is only the momentum p. So all these constants just stay as constants. And this expression should seem familiar from classical mechanics, right? Because classical mechanics, we have dx by dt is p over m. So for the harmonic oscillator, we can see that the change in the expectation values of the quantum mechanical values is the same as the classical analogues. Now let's see if this also holds for the momentum. To do for the momentum, we need to evaluate hp, which is a half k x squared p, as once again the momentum squared term we would have would vanish as p squared and p commute. Now using the same rule as here, you can then write a half k x commutator of x and p plus commutator of x and p x. Now this time is plus IH bar. Again, we have two of them, so that we finish out with IH bar k x. If we plug this into our formula here, we get that the change in the expectation value of the momentum with time is just minus k expectation value of x. And once again, the expectation value just of x, because that's the only thing that's variable. Once again, this should be familiar from classical mechanics, where we say that dp by dt is the force, which is just minus the derivative of the potential with respect to x. And since the potential for the harmonic oscillator is a half kx squared, this is just minus kx. So for the momentum, we can see as well that the change of the expectation values in quantum mechanics yield the same result as the classical analogues. This is a special case for the harmonic oscillator, but it's very nice to demonstrate the Ehrenfest theorem.